Okay, so in this video, we're going to be doing an example on how to solve a Navier-Stokes problem. Okay, so the Navier-Stokes equations, these are our partial differential equations that allow us to solve for the conservation of mass and momentum in a fluid. And if you solve these equations, what you get is our functions that show the velocity and sometimes the pressure within the fluid. But solving these problems can be quite an ordeal, and so I wanted to do an example just to show you how you go about solving this by hand on a simple problem. Okay, so here's our simple problem, and so this is a very classical type flow, so it's called Couette flow, and so this is basically the flow between parallel plates where one of the plates is moving. Okay, so here's our situation. So we have two plates that are parallel, and the top plate is moving with a velocity u plate, okay, and the bottom plate is fixed. And so what we want to do for this problem is we want to compute the distribution of velocity u of y inside this channel. Okay, so for this problem, we can actually jump straight to the momentum equation. And the first step is to start canceling out some terms due to assumptions, right? And so with this full equation here, it's way too long for us to solve as it is. And so we need to simplify this before we can get started. Okay, so here are all the assumptions we can apply for this problem. I've kind of done that all in one step, but I've color-coded, which assumptions go by canceling out which terms, just so that you can kind of know what to do. Okay, so there's quite a lot of assumptions, and so the first assumption is incompressibility. So that doesn't knock out any terms, but it's necessary for us to use this form of the equation. Okay, the second assumption is steady flow, and so that knocks out the time derivative term. Next is the assumption of 1D flow, and so any velocity components that are not in the x direction, v and w, we're going to cancel those as well. Okay. For this problem, we're going to assume no pressure gradient and no gravity. And so actually, if you read the problem statement on the previous slide, it stated that there's no pressure gradient. And the fact that the flow is horizontal, that means we have no gravity force as well. Okay. Next, we're going to assume fully developed flow. That means any derivatives on the velocity that are with respect to x, we're going to set that equal to 0. Okay. Alternatively, you can get that same assumption by following the continuity equation and applying assumption 3. Okay. And then finally, we need to cancel out the very last term, the derivative with respect to z, using a planar flow assumption. Okay, so what we're left with after all that carnage is just one single term, which is just the viscosity term in the y direction. Okay, and so the nice thing about this is that this is a simple equation that we can solve just by direct integration. Okay, so but before we do that, let's go ahead and state our boundary conditions. And so we have two solution type boundary conditions here. And so first we have a fixed wall at the bottom plate, and so that sets our velocity equal to 0 there because of the no slip condition. And then on the top plate, we are again going to apply a no slip boundary condition, but since this wall is moving, that means the fluid that's touching that wall has to move as well. Okay, and so we're going to set the velocity at the top of the plate equal to u, or top of the channel equal to u plate. Okay, so now let's go ahead and solve for the solution. And so we're starting with this equation here, which is just the second order derivative of u with respect to y is equal to 0. So we can solve this by direct integration. So let's go ahead and perform an integral on both sides. And so on the left-hand side, what that's going to do is that it's going to cancel out one of the derivatives, and so you end up with just a first-order derivative, du dy. And on the right-hand side, when you integrate 0, you get 0. But because we're doing indefinite integrals, we have to add this arbitrary constant c1. Okay. And so let's go ahead and do that again. And since we're not quite at u yet, so we can integrate one more time. Okay. And if we integrate one more time, then the left-hand side just becomes u of y, which is what we want, and the right-hand side becomes a linear function c1y plus c2. Okay. And so now we're ready to apply boundary conditions. So let's go ahead and do that. And so our first boundary condition here is u of 0 is equal to 0. And so we're going to plug in y is equal to 0 in our equation and set the whole thing equal to 0. And then by doing that, we find that c2 is equal to 0. And then our other boundary condition here is that the velocity at the top of the plate is equal to u plate. Okay, so we're going to set y is equal to h and then set that equal to u plate. And then what we get from this is that c1 is equal to u plate divided by h. And then from there, we're able to put together our full solution. So u of y is equal to u plate over h times y. And so you can see here in the case when we have no pressure forcing and we just have moving plates, our solution is just a linear function in y. And that's kind of the characteristic, characteristic of the coolant flow.